Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So if I handed you a master catalog of, say, 6,000 newly discovered alien worlds, you would naturally expect to see planets of pretty much every conceivable size, right?
Yeah, exactly. I mean, it just makes intuitive statistical sense.
Right. We're sort of wired to expect this cosmic bell curve. You'd assume there'd be a few tiny planets, the size of Mercury, and then this absolute mountain of average, mid-sized planets right in the middle of the graph.
And then, of course, the trailing off of massive gas giants like Jupiter at the far end.
Exactly. But when astronomers actually plotted out the real-world measurements of all these exoplanets that humanity has discovered over the last few decades, they didn't find a smooth, elegant bell curve at all.
No, not even close.
They found a ghost town. Like an impossibly massive, glaringly empty gap right in the middle of the data where planets that are exactly 1.8 times the size of Earth simply do not exist.
Right. And today, we are really getting into the invisible cosmic hand that is essentially actively erasing these worlds.
Because the statistical impossibility of that gap, it really cannot be overstated.
Oh, absolutely not.
Yeah.
When you look at the raw data, you see this massive population of planets peaking around 1.3 to 1.5 times the radius of Earth.
Okay.
And then there's another distinct, just massive population peaking around 2.4 to 2.8 Earth radii.
But right at that 1.8 mark?
The distribution just plummets. We call it the radius valley.
The radius valley.
Yeah. And this bimodal distribution, this really stark division of the cosmos into two very specific planetary sizes is, arguably the greatest unresolved mystery in modern planetary science.
And I want to make sure you, the listener, understand exactly what is at stake here. This isn't just a conversation about obscure astronomical bookkeeping,
Definitely not.
We're not just categorizing space rocks for the sake of a spreadsheet. We are talking about deciphering the fundamental underlying thermodynamic and gravitational laws that govern planetary destiny.
Because whatever violent mechanism is forcing these planets into these two separate camps, it ultimately dictates whether a solar system is even capable of producing a habitable world.
Right. If we don't understand the physics carving out this valley, our entire understanding of the galactic real estate market is flawed.
It completely changes how anomalous our own Earth might be. It forces us to ask, well, are the planets we see today the same planets that were born billions of years ago?
Because we're just looking at an end state.
Exactly. The radius valley tells us that either the universe physically cannot manufacture planets at that 1.8 size due to some limitation in the building materials, or the universe does manufacture them. But some aggressive evolutionary force systematically destroys or radically alters them over time.
So we're dealing with a literal cosmic sorting mechanism. Below the valley, we have the super-Earths, and above the valley, we have the sub-Neptunes.
That's the split, yeah.
Before we debate how they got sorted, we have to understand what these two categories actually look like on the ground. Like if I'm standing on a super-Earth, what are the actual geophysics happening beneath my boots?
Well, you are standing on a dense, rocky sphere of compressed iron, nickel, and silicate mantle.
Okay, so just a giant rock.
Basically, yeah. Compositionally, super-Earths are just scaled-up terrestrial worlds. But the physics of a scaled-up Earth completely changed the surface environment.
How so?
At roughly 1.5 times Earth's radius, assuming a rocky density, the mass of that planet scales by the cube of its radius.
Oh, wow.
So you're dealing with a world that might be 3, 4, even 5 times the mass of Earth. The surface gravity would be just bone-crushing.
And I imagine the atmosphere is pretty intense, too.
If it has a thin secondary atmosphere like Earth or Venus, the pressure is dictated entirely by that intense gravitational well. Tectonic activity could be wildly exaggerated or the immense lithospheric pressure could completely lock the crust, preventing plate tectonics entirely.
Okay, so it's a giant, heavy, potentially locked rock. But then we leap across this empty 1.8 radius valley, and we land on a sub-Neptune.
Right.
These are planets sitting at, say, 2.5 times the size of Earth. Are they just even bigger, heavier rocks?
Not at all. And that is, the crucial differentiator here.
Okay.
When we measure the mass of these sub-Neptunes using radial velocity, basically observing how much their gravity tugs on their host stars.
Right, the wobble method.
Exactly.
Yeah.
And then we calculate their volume based on how much starlight they block. Well, their overall bulk density just plummets. They're incredibly puffy.
So they aren't solid surfaces.
No. The data dictates that a significant fraction of a sub-Neptune's volume must be made up of low-density materials. Deep down in the center, there is almost certainly a rocky or metallic core, similar in mass to a super-Earth.
But wrapped around it.
An immense extended envelope of primordial gas. We're talking about massive atmospheres of hydrogen and helium, the lightest elements in the universe.
Or potentially incredibly thick layers of lighter molecular ices and fluids, right?
Yes, exactly. You couldn't land a ship on a sub-Neptune. You would just sink through a cloud deck.
Like falling into Jupiter?
Pretty much. You'd descend into an atmosphere where the pressure and temperature increase exponentially until the gas becomes a supercritical fluid, and that just blurs the line between liquid and gas entirely.
I'm trying to visualize this bimodal gap, and the closest analogy I can come up with is like a clothing factory.
Clothing factory. Okay, I like that.
Yeah, it's like walking into a massive warehouse that produces millions of shirts, but you walk down the aisles and you only see racks of size small and racks of size large.
And no mediums.
There isn't a single medium shirt in the entire building. So the question naturally becomes, is the factory completely incapable of physically stitching together a medium shirt?
Meaning the raw materials at the start of the assembly line prevent it.
Exactly. Or is the factory churning out millions of mediums, but there's something wrong with the fabric? And over a few years, they either shrink in the wash into smalls, or the fibers break down and they stretch out into larges.
The manufacturing defect versus the evolutionary degradation.
Yeah.
That really captures the exact schism dividing the astronomical community right now.
Well, before we get to those two competing theories, I have a theoretical question.
Sure, go for it.
If the universe actively avoids this 1.8 radius middle ground, what would a planet exactly that size actually look like if one magically managed to exist?
Oh, that's a great question.
Like if you took the dense, heavy rock of a super-Earth and the puffy, volatile envelope of a sub-Neptune and forced them into a 1.8 radius compromise, what kind of world is that?
It would be a world at war with its own internal physics.
Really?
Yeah, at exactly 1.8 Earth radii, assuming a standard rocky core mass, you're sitting precisely on a thermodynamic and gravitational razor's edge.
Okay, so it's precarious.
Extremely. The planet has managed to accrete a thin envelope of hydrogen and helium gas, perhaps just 1 or 2% of its total mass.
But because that gas is so incredibly light and puffy,
It accounts for a massive percentage of the planet's total volume.
so it's a rocky core wearing a giant bloated jacket of gas.
Yes, but the jacket doesn't fit properly.
I love that.
The gravity of the rocky core is locked in a constant, delicate tug of war against the thermal kinetic energy of the gas molecules. The hydrogen atoms want to bounce away, heated by the star, while the core tries to pull them back.
So a 1.8 Earth radius planet is just fundamentally unstable.
Any slight alteration in its environment, a slight increase in stellar radiation, a minor orbital shift, even a slow loss of internal planetary heat, and that delicate balance collapses.
And what happens when it collapses?
The mechanism either strips the gas away entirely, leaving a bare rock, or the planet was massive enough to hold on to a much thicker jacket from the start, making it a much larger sub-Neptune.
The 1.8 radius size is essentially a transition zone of instability,
Precisely. It just can't hold that state.
which perfectly sets up the two warring factions in astrophysics trying to explain this exact instability. Let's tackle hypothesis 1, the shrinking gas dwarf theory.
Okay, the evolutionary model.
Right, the idea that the factory actually is making medium shirts, but they are shrinking in the wash.
The shrinking gas dwarf model posits that the radius valley is not a feature of planetary birth, but an evolutionary scar carved into the galactic population over hundreds of millions of years.
Okay.
The core assertion here is radical in its simplicity. It says that super-Earths and sub-Neptunes are actually the exact same species of planet.
Wait, if they're the exact same species, how do we get the bimodal gap? If every planet starts the same, we should see a continuum.
Because of where they end up living.
Okay, explain that.
Under this hypothesis, during the chaotic early days of a protoplanetary, the swirling cloud of dust and gas around a newborn star, every rocky core that reaches a certain mass begins to aggressively sweep up the abundant hydrogen and helium gas from the nebula.
Right, so they're sucking up all that material.
Yeah, they all wrap themselves in those thick, puffy envelopes. They were all born as sub-Neptunes, every single one of them.
So the factory only makes large shirts.
Exactly.
Okay, so the universe is initially populated entirely by these puffy gas dwarfs. Where do the super-Earths come from?
From the violent temper of young stars.
Oh, right. Young stars are basically toddlers.
Very angry toddlers. A newly ignited star is not the calm, steady yellow dwarf like our sun is today. Young stars, particularly in their first 100 million years, are highly volatile.
They're spitting out a lot of energy.
Incredibly intense fluxes of extreme ultraviolet, or EUV, radiation, and incredibly powerful stellar winds.
And EUV radiation interacts with atmospheres differently than visible light, right?
Drastically differently. Visible light largely passes through an atmosphere, warming the surface. That extreme ultraviolet radiation is entirely absorbed by the very uppermost layers of a planet's atmosphere.
Like the thermosphere and exosphere.
Yes. When hydrogen and helium atoms absorb these high-energy EUV photons, the atoms undergo rapid photoionization and intense heating.
So we are talking about superheating the outermost layer of the planet's gas envelope.
We're talking about raising the kinetic energy of those gas molecules to an extreme degree. Temperature at an atomic level is just velocity. It's how fast the atoms are vibrating and bouncing around.
Right, getting them all energized.
Exactly. If a young planet is orbiting close to its host star, the EUV radiation dumps so much thermal energy into the upper atmosphere that the velocity of the hydrogen atoms begins to exceed the escape velocity of the planet's gravity.
I usually picture atmospheric loss like a slow leak in a tire. Just, molecules occasionally drifting off into space one by one.
What you're describing is Jean's escape, which is a slow thermal process.
Okay.
But close to a young flaring star, the mechanisms shift to something called hydrodynamic escape.
Hydrodynamic escape? That sounds aggressive.
It is. It is not a slow leak. The heating is so intense and so rapid that the entire upper atmosphere expands outward as a bulk fluid. The outward pressure of the heated gas completely overwhelms the planet's gravity. It creates a continuous massive planetary wind. The atmosphere literally boils off into the vacuum of space,
carrying away vast percentages of the planet's mass over millions of years.
Exactly.
This completely reframes how I think about a super-Earth. If this theory holds, a super-Earth isn't a planet that formed from rocky material.
No, it's not.
It's a sub-Neptune that was fundamentally stripped naked.
It is the surviving bare rocky core of a dead gas dwarf.
Wow. It's like holding a giant fluffy marshmallow far too close to a roaring, out-of-control campfire.
That's actually a great way to picture it.
At first, the marshmallow is huge and puffy, but the intense, radiant heat of the fire causes the outer layers to catch fire, melt, and evaporate. You sit there holding it, and eventually the entire white, fluffy exterior burns away completely.
Leaving you with nothing but that dense, blackened, hard core of caramelized sugar stuck to the stick.
Yes. The marshmallow is the sub-Neptune. The campfire is the young star's extreme ultraviolet radiation. And the blackened core that survives is the super-Earth.
The analogy holds up surprisingly well to the thermodynamic realities. And crucially, it explains the spatial distribution we observe.
How so?
The planets that formed or migrated too close to the campfire experienced catastrophic hydrodynamic escape. Their hydrogen envelopes evaporated and their radii shrank from 2.5 Earth radii down to 1.3 or 1.5.
They crossed the valley.
Yes. The planets that happened to orbit further away at a safe distance where the EUV radiation was less intense retained their gas envelopes. They remained puffy sub-Neptunes.
But hold on, let me push back on this. If it's just a matter of distance from the star, stellar radiation should decrease smoothly according to the inverse square law, right?
It does, yes.
It just gets gradually weaker the further you go. So if the radiation gets gradually weaker, shouldn't atmospheric loss be a gradual gradient?
I see where you're going.
Why wouldn't we see a ton of partially boiled marshmallows? Why a perfectly empty gap exactly at 1.8 radii? Shouldn't there be planets that lost half their atmosphere and just stopped right in the middle?
That is the exact mathematical hurdle the shrinking gas dwarf theory has to solve. And the answer lies in the exponential nature of atmospheric retention.
Okay, unpack that for me.
Gravity does not scale linearly with the thickness of a gas envelope. Because hydrogen is so light, the difference between an envelope that makes up 1% of the planet's mass and an envelope that makes up 5% of its mass.
It results in a massive difference in physical volume, right?
Exactly. If a planet loses enough gas to shrink to 1.8 Earth radii, the remaining gas envelope is incredibly tenuous. It is highly extended and weakly bound to the rocky core.
So it's essentially a tipping point.
Precisely. Once hydrodynamic escape manages to strip an atmosphere down to that critical 1.8 radius threshold, the planet's gravitational grip on the remaining gas becomes so pathetic that the rest of the atmosphere is lost incredibly rapidly.
Oh, I get it. It doesn't pause in the valley, it falls off a cliff.
Yes. The planet accelerates through the 1.8 radius size in a blink of cosmic time, shrinking rapidly down to the bare rock.
So the valley is empty because planets physically cannot maintain stability at that size under stellar irradiation.
Exactly. It's an unstable equilibrium.
It is an incredibly elegant theory. It uses brutal, violent astrophysics, atmospheric boiling, extreme ultraviolet radiation, orbital dynamics to explain a simple statistical anomaly.
It really is a beautiful model.
But as compelling as the shrinking gas dwarf theory is, it relies entirely on the assumption that every planet starts as a puffy gas world.
And that's where the contention lies.
Right. And I know there is an entire competing faction of planetary geologists and astrophysicists who look at that exact same bimodal graph and declare that the evolutionary theory is completely backwards.
Which introduces hypothesis 2. The dense water worlds.
Okay, let's get into the rival camp.
This theory discards the shrinking in the wash concept entirely. This faction argues that the Radius Valley is not a graveyard of stripped atmospheres. It is a fundamental imprint of planetary birth.
The factory never made the medium shirts.
Exactly. Super-Earths and sub-Neptunes are born radically, fundamentally different from day one, using completely different raw materials.
But if they are born in the same solar system, how do they get access to completely different raw materials? They are forming out of the exact same protoplanetary disk.
They are forming in the same disk, but the thermodynamic environment inside that disk changes violently depending on your radial distance from the infant star.
Okay.
The key to this entire hypothesis hinges on an invisible boundary line within the disk called the snow line, or the ice line.
We need to really dive into the mechanics of this snow line, because this feels like the linchpin of the whole debate. What physically happens at this boundary?
To understand the snow line, you have to look at the temperature gradient of the protoplanetary nebula. Right next to the young star, the ambient temperature of the swirling gas and dust is thousands of degrees.
It's a furnace.
A total furnace. In that environment, volatile compounds, specifically water, ammonia, and methane, cannot exist in a solid state. The thermal energy is just too high. Water exists exclusively as a superheated vapor.
So it's basically just humidity in space.
Precisely. And vapor cannot clump together to build a planet.
Makes sense.
Therefore, the only materials capable of condensing into solid grains in the inner solar system are heavy elements with incredibly high melting points. Iron, nickel, silicates, rocks.
So planets that accrete close to the star inside the snow line are forced to build themselves entirely out of dry, refractory material.
Yes, they become rocky super-Earths.
But as you move further away from the star, the temperature of the nebula drops.
It drops significantly. And eventually, at a specific distance, perhaps 2 or 3 times the distance Earth is from the sun, the temperature of the vacuum crosses a critical thermodynamic threshold.
Which is what, exactly?
About 150 Kelvin.
Huh?
At this temperature, water vapor undergoes desublimation. It transitions directly from a gas into microscopic solid ice grains.
You cross the snow line and suddenly it's snowing in space.
Literally. The amount of solid mass available to build planets suddenly spikes massively. Water is one of the most abundant molecules in the universe.
Right. But inside the snow line, it's useless vapor.
Exactly. But outside the snow line, it is solid building blocks. Planets forming out there aren't just accreting dust and rock. They're sweeping up billions of tons of solid ice.
Okay, so this hypothesis argues that the sub-Neptunes we observe today are not rocky cores hiding inside massive hydrogen envelopes.
Right. They are dense water worlds that formed beyond the snow line, heavily enriched by ice, and then later migrated inward toward the star.
Okay, when you say water world, my brain instantly goes to Earth. We literally call Earth the blue marble. We have the Pacific Ocean.
Right, but structurally, Earth's water is basically a wet coat of paint.
Exactly. If you look at the total mass of our planet, water makes up roughly 0.02%. It is a statistical rounding error compared to the iron core and the silicate mantle.
It's tiny.
So how much water are we talking about for one of these sub-Neptunes?
The mass fraction calculations for these dense water worlds suggest they could be comprised of 50% rock and 50% water by mass.
50% water by mass, that completely defies comprehension.
It's staggering.
I can't even picture what the structural geophysics of a planet composed of half water and half rock would entail. If a planet is 2.5 times the size of Earth and half of its mass is water, wouldn't that ocean just be thousands of miles deep?
Oh, absolutely.
Does it even have a rocky ocean floor?
The physical reality of a 50% water mass planet is far stranger than just a deep ocean. You have to consider the hydrostatic pressure. Gravity on a planet of that size is pulling all that massive amount of water toward the center. As you dive down through the liquid surface ocean, the pressure increases exponentially.
Like reaching the bottom of the Mariana Trench, but way worse.
Orders of magnitude worse. Long before you ever reach the rocky core, the pressure becomes so utterly immense that the water molecules are physically forced to rearrange their structural lattice.
Wait, forced to rearrange, meaning the water stops being liquid.
The pressure overrides the temperature. Even if the internal temperature of the planet is thousands of degrees far past the normal boiling point of water, the sheer crushing weight of the ocean above physically prevents the water molecules from moving freely.
So what happens to them?
They lock into highly exotic crystalline solid states. We are talking about high-pressure phases of ice like ice 7, ice 10, or supersonic water.
Hot, solid ice. That sounds like a contradiction in terms. What exactly is supersonic water?
It is a bizarre phase of matter where quantum mechanics and fluid dynamics intersect. Under millions of atmospheres of pressure, the oxygen atoms in the water molecules lock into a rigid, solid, crystalline lattice.
Okay, so a solid frame.
But the pressure is so intense that the hydrogen atoms decouple. The hydrogen protons become completely delocalized and actually flow freely through the solid oxygen lattice, acting almost like electrons in a metal.
So you have a solid matrix of oxygen with liquid hydrogen flowing through it.
Exactly. It conducts electricity like a metal. A dense water world wouldn't have a normal ocean floor.
What would it have?
It would have a surface envelope of supercritical steam, transitioning into a vast, crushing liquid ocean, which eventually solidifies into thousands of miles of glowing metallic supersonic ice.
Glowing metallic ice.
And that's wrapped around whatever rocky core lies at the very center. The magnetic fields generated by a spinning mantle of supersonic water would be incredibly complex.
I can't even imagine.
They'd likely be non-dipolar, meaning they might have multiple north and south poles scattered all across the planet.
That is genuinely one of the most alien things I have ever heard.
It's wild physics.
But let me bring this wildly exotic geology back to the core mystery. How does building a 50-50 supersonic water world explain the 1.8 radius valley?
Good question.
If planets form from dry rock inside the snowline and half ice outside the snowline, why wouldn't we just see a mix of sizes? Why the stark gap?
The gap is created by the physical limits of the materials themselves. Imagine playing with building blocks.
Okay.
If you only have high-density dry rock available inside the snowline, there is a maximum size a rocky planet can realistically reach before it runs out of material in its local orbital lane.
Makes sense.
Based on planetary accretion models, the maximum physical size a dry rocky super-Earth generally achieves is roughly 1.4 to 1.5 times the radius of Earth. To get bigger than that with purely dry rock requires highly improbable collision events.
Okay, so the rock planets naturally cap out around 1.5.
Exactly. Now, on the other side of the snowline, you have an abundance of low-density ice. Because ice is far less dense than rock, a planet composed of 50% water and 50% rock is naturally going to be physically larger than a pure rock planet of the exact same mass.
Right. A half-water world simply takes up more volume.
Because water isn't as dense as iron.
Exactly.
And because water is so abundant out there, these planets accrete massive amounts of it very quickly. The minimum physical size of a planet born with that 50-50 ice rock composition tends to naturally inflate the planet's radius to roughly 2.4 to 2.6 times the size of Earth.
Ah, I see it now.
Yeah.
The valley isn't an evolutionary scar. It's an empty space between two completely different recipes. Nature can bake a pure rock planet up to size 1.5, and when nature bakes a half-water planet, it puffs up to at least size 2.4?
Precisely. Under Hypothesis 2, the bimodal distribution directly maps to the snowline. There are no 1.8 Earth radius planets because neither the dry recipe nor the wet recipe physically results in a planet of that specific volume.
No atmospheric stripping is required.
No planetary sunburns. just an invisible thermodynamic boundary in the primordial disk dictating planetary destiny based on available building materials.
So we have reached an incredible scientific impasse. The observational data, the empty 1.8 gap, is undisputed. But we have two fiercely competing camps with completely opposing explanations.
Both with very solid math.
Right. Hypothesis 1 says it's hydrodynamic atmospheric stripping boiling sub-Neptunes into super-Earths over millions of years. Hypothesis 2 says it's the snow line forcing planets to be born as either small dry rocks or massive superionic water worlds.
Exactly.
Both models utilize rigorous thermodynamic physics. Both models mathematically account for the bimodal distribution. Both models sound perfectly plausible. As an astronomer, how do you possibly settle a debate when the existing data set supports both factions equally well?
Well, the only way to break a deadlock in historical sciences and planetary formation is ultimately a historical science, is to find a way to look back in time.
Okay, how do we do that?
We're currently looking at a population of exoplanets that are billions of years old. We're looking at the final product. To definitively prove which mechanism is responsible, we have to catch these systems in the act of forming.
Right.
We have to find and observe extremely young exoplanets.
That logically makes perfect sense. If hypothesis 2, the water world theory, is correct, then the super-Earths and sub-Neptunes are born completely distinct.
Correct.
So if we look at a solar system that was literally just born, we should see the bimodal gap already firmly established. The super-Earths will already exist.
Yes, and conversely, if hypothesis 1, the shrinking gas dwarf theory, is correct, the valley shouldn't exist yet.
Because the hydrodynamic escape mechanism takes hundreds of millions of years to fully boil away a hydrogen envelope.
Precisely. So, if we look at a newly formed stellar system, we should see absolutely no bare, rocky super-Earths. We should see a completely unbroken population of massive, puffy sub-Neptunes just waiting for the star to slowly strip them down.
The test is so clean, it's a binary outcome. So why is this even a debate? Why haven't the astronomers just pointed their telescopes at the stellar nurseries, cataloged the baby planets, and published the answer?
Because the universe actively fights our attempts to observe its infancy. We have collided with a monumental observational catch-22.
Really?
Yeah. Identifying and characterizing young exoplanets is one of the most excruciatingly difficult tasks in modern observational astrophysics. Let's look at the harsh statistical reality of our current catalog. We have confirmed roughly 6,000 exoplanets across the galaxy.
Okay.
Do you know how many of those 6,000 are definitively characterized as young?
Well, first define young in an astrophysical context, because to us, the dinosaurs dying out 65 million years ago is ancient history.
Fair point. In stellar evolution, 50 million years is the crucial window. For a star like our Sun, which has a main sequence lifespan of 10 billion years, 50 million years is absolute infancy.
Okay, just a baby.
The protoplanetary disk of gas and dust has only recently dissipated, clearing our line of sight. The planets have finished their primary accretion, but the long-term evolutionary mechanics like atmospheric stripping haven't had enough time to drastically alter the landscape.
So 50 million years is the exact temporal sweet spot we need to test these theories.
Exactly.
Okay, so 50 million years is the cutoff. Out of the 6,000 planets we know about, how many fit that alibi?
Roughly 20.
20 out of 6,000.
It is a statistically insignificant rounding error.
But why? Is it just a matter of telescope time, or are we not looking in the right places?
Not exactly.
I mean, if we know where the stellar nurseries are, like the Orion Nebula or the Pleiades, why can't we just dedicate the James Webb Space Telescope or the Kepler archives to stare specifically at those clusters and find the planets?
Because young stars are actively hostile to the methods we use to find planets. This isn't a problem of telescope aperture. It is a problem of signal-to-noise ratio.
Okay, break that down for me.
To understand why we only have 20 young planets, you have to understand the sheer chaos of a young stellar environment. The primary method humanity uses to discover exoplanets is the transit photometry method.
That's the method where we wait for a planet to pass in front of a star and measure the microscopic shadow it casts, right? The star dims slightly.
Yes. We measure the photometric light curve. We stare at a star, establish a baseline of its brightness, and wait for a tiny periodic U-shaped dip in that brightness caused by an opaque spherical object, the planet eclipsing a fraction of the stellar disk.
And the size of the dip tells us the size of the planet.
Exactly. The transit depth is proportional to the square of the ratio of the planet's radius to the star's radius. It is incredibly precise geometry.
So what's the problem?
This method fundamentally requires the star itself to be stable. If you are looking for a dip in light that is a fraction of a percent, the flashlight you are staring at needs to emit a perfectly constant beam.
And young stars are not constant.
Young stars are violent, temperamental, magnetic nightmares. They really are. They are rapidly spinning, meaning their internal dynamos are operating in overdrive. Their magnetic fields twist and snap, creating massive acoustic and magnetic disturbances across the photosphere. They are covered in giant star spots, dark, cool regions of immense magnetic pressure.
Like our sunspots, but scaled up.
Scaled up by orders of magnitude. And as the young star rotates, these massive dark spots rotate into our field of view and then disappear around the other side. This causes the overall brightness of the star to fluctuate wildly.
Oh, I see.
From our perspective on Earth, a rotating star spot causes a dip in the light curve that looks agonizingly similar to a transiting planet.
So it generates thousands of false positives. You think you've found a young planet, but it's just a magnetic blemish on the star rotating past.
It gets worse.
Of course it does.
Young stars also flare constantly. Magnetic reconnection events release massive, instantaneous bursts of thermal energy and radiation. These flares create sudden, massive spikes in the light curve.
So the data is a mess.
If you point a standard optical telescope like Kepler or TESS at a 20-million-year-old star cluster, the resulting photometric data doesn't look like a flat line with occasional neat dips. It looks like the seismograph of a magnitude 9 earthquake.
Wow.
It is a jagged, chaotic, violently noisy mess. Trying to find the delicate 0.1% U-shaped dip of a transiting sub-Neptune hidden inside the blinding spikes of flares and the rolling hills of star spots is fundamentally impossible with standard optical sensors.
The star's own intrinsic noise completely grounds out the planetary signal.
Exactly.
We are trying to listen to the delicate ring of a silver bell in a room where a teenager is testing out a wall of heavy metal amplifiers.
That is a perfect articulation of the problem, and that is why we are stuck with only 20 young planets. Our general-purpose telescopes simply cannot filter the heavy metal.
Right.
To solve the radius valley, we can't just look harder, we have to look differently. We need a tool custom-built to silence the stellar noise.
Which brings us to the ultimate architectural response to this crisis, the proposed blueprint for the Early Evolution Explorer, or EVE.
Yes, EVE.
This is a mission concept specifically designed from the ground up to solve the Radius Valley Catch-22. Let's break down the mission parameters of EVE, because the scale of ambition here is just staggering.
EVE is not designed to be a general observatory. It is a highly specialized, targeted, single-purpose instrument. Its sole objective is to drastically increase the census of characterized planets younger than 50 million years.
Okay, so how does it do that?
To achieve this, the EVE mission proposes targeting 30 specific known fields of young stellar clusters.
It's pointing a sniper rifle directly at the cosmic maternity wards.
And the observational timeline is rigorous. The spacecraft is designed to stare at each of these 30 distinct fields continuously without interruption for 30 days straight.
30 days of uninterrupted staring at a single patch of sky. That's intense.
Over its proposed 2.5-year primary mission lifespan, EVE aims to capture high-precision photometric light curves from roughly 20,000 newly formed stars.
Let's talk about those numbers. 20,000 young stars is an incredible sample size compared to the 20 planets we currently have. But to get there, why the need for 30 days of continuous staring? Why not just scan the sky rapidly?
Because of the orbital mechanics of the transit method. If a planet is orbiting a young star every 10 days, it only transits the star casting that shadow for a few hours during that 10-day orbit.
Okay, so you have to catch it right at that moment.
Right. If you only look at the star once a week, you have a massive probability of missing the transit entirely. And to confirm a planet, you can't just see one dip. You need to see at least 3 periodic dips to prove it's an orbiting body and calculate its orbital period.
So staring continuously for 30 days guarantees a 100% duty cycle, ensuring you catch multiple transits for any planet orbiting close to the star.
It maximizes the geometric probability of catching the shadow.
But what I find truly fascinating about the EVE mission architecture is what they explicitly intend to ignore.
The exclusion list, yeah.
The proposal dictates that the mission will focus exclusively on small planets, sub-Neptunes, and super-Earths, and it will actively, deliberately exclude any search for hot Jupiters.
Yes. It is a strict mandate of the data processing pipeline.
I have to push back on that logic.
Huh?
Hot Jupiters are massive gas giants orbiting incredibly close to their stars. They block a huge amount of light. They're the easiest targets to spot.
True.
If you are building a multi-million-dollar space telescope and staring at 20,000 stars, why in the world would you intentionally configure the software to ignore the biggest, most obvious discoveries? It feels like going on an African safari with a state-of-the-art camera and actively turning it off every time an elephant walks by so you can focus on photographing a specific species of beetle. Why ignore the elephants?
Because the elephants do not help you answer the fundamental question driving the mission. EVE is not a fishing expedition meant to catch everything in the ocean. It is an experiment designed to test a specific thermodynamic hypothesis.
But aren't hot Jupiters relevant?
Hot Jupiters are fascinating, sure, but their formation and evolutionary pathways are entirely distinct from the small, rocky planets involved in the Radius Valley debate.
How so?
Because of their sheer mass. A hot Jupiter is so incredibly massive, hundreds of times the mass of Earth, that its gravitational well is virtually insurmountable.
Okay.
Even if a hot Jupiter orbits blisteringly close to a young flaring star, the extreme ultraviolet radiation is completely incapable of inducing hydrodynamic escape.
Oh, because it's just too heavy.
Exactly. The gas molecules can never reach escape velocity because the planet's gravity is too powerful. A hot Jupiter does not boil away.
So they don't shrink.
Right. Therefore, hot Jupiters have absolutely zero relevance to the shrinking gas dwarf theory or the water world theory. Searching for them, cataloging their transits, and processing their light curves would consume incredibly valuable computational bandwidth and data downlink capacity that must be preserved for the faint, microscopic signals of the sub-Neptunes.
It is an exercise in rigorous scientific discipline.
It really is. EVE ignores the elephants to ensure it doesn't miss a single beetle.
Okay, the discipline makes sense. Preserve the bandwidth for the targets that actually matter. But that brings us right back to the central problem we just discussed.
The noise.
Even if EVE is staring continuously for 30 days, and even if it's focused entirely on small planets, it is still staring at 20,000 violently chaotic, flaring, spotted young stars. The data is still going to look like an earthquake seismograph.
Absolutely.
How does EVE's telescope design actually solve the heavy metal problem? How does it filter the stellar noise to find those tiny dips?
EVE solves it through an ingenious application of multi-band photometry. The spacecraft doesn't just have one camera lens staring at the star. It utilizes a three-sensor solution.
3 sensors.
It splits the incoming starlight and feeds it simultaneously into 3 distinct detectors, each calibrated to measure a completely different wavelength of the electromagnetic spectrum.
Okay.
It has a near-ultraviolet sensor, an optical sensor, which sees the visible light we see, and a near-infrared sensor.
The 3-sensor solution. Why is splitting the light into ultraviolet, optical, and infrared the key to canceling out the stellar noise?
It hinges on the physical differences between a geometric shadow and a thermodynamic energy burst. Let's look at the planet first.
Sure.
A transiting planet is an opaque physical object. When it passes in front of the star, it blocks the star's light. Crucially, a rock blocks ultraviolet light just as effectively as it blocks optical light and infrared light.
Because a shadow is dark across the entire spectrum.
Correct. If a dip in the light curve is caused by a real planet, that exact same U-shaped dip will register simultaneously on the ultraviolet sensor, the optical sensor, and the infrared sensor. The drop in flux is uniform across all wavelengths.
But a solar flare isn't a shadow?
A stellar flare is an explosive magnetic reconnection event. It is a massive sudden release of thermal energy. And the physics of blackbody radiation and emission spectra dictate that this sudden release of energy is not distributed evenly across the electromagnetic spectrum.
Oh, I see where this is going.
When a young star flares, the vast majority of that released energy spikes violently in the high-energy, short-wavelength end of the spectrum. Specifically, flares shine incredibly brightly in the near-ultraviolet band.
Ah, so the ultraviolet sensor isn't there to find the planet.
Exactly. The near-ultraviolet, or NUV, sensor acts as a highly sensitive flare alarm system. When the star throws a tantrum, the NUV sensor registers an enormous, unmistakable spike in ultraviolet flux.
And the other sensors.
Meanwhile, the optical and infrared sensors might only register a moderate, confusing bump. By continuously monitoring the NUV channel, the mission's onboard computers know exactly when a flare is happening, exactly how intense it is, and exactly how its energy distribution should bleed into the optical channels.
So it isolates the heavy metal music.
Exactly. The EVE data processing pipeline takes the jagged, screaming ultraviolet light curve, uses it to map the exact temporal profile of the star's magnetic activity, and then mathematically subtracts that modeled activity from the primary optical light curve.
That is brilliant.
It essentially runs a complex detrending algorithm, using the NUV data as a negative filter against the optical data.
This is literally active noise cancellation technology applied to stellar astrophysics.
The photometric principles are very similar to acoustic phase cancellation, yes. The NUV sensor is the external microphone on your headphones, listening to the ambient noise of the airplane engine or the heavy metal music. The computer flips the waveform of that noise and feeds it back into the audio stream, canceling the engine out. EVE uses the NUV sensor to listen to the stellar flares, calculates the photometric equivalent of the reverse waveform, and applies it to the optical data.
Imagine the feeling in the control room the first time they run that algorithm on real data. You are staring at this raw, unreadable graph of optical light. It looks completely chaotic. No human eye could ever discern a pattern in it.
Just spikes in noise.
And then you click a button to execute the NUV subtraction protocol. The computer strips away the magnetic noise, and right before your eyes, the jagged, chaotic spikes flatten out, the rolling star-spot hills smooth out into a clean baseline, and sitting perfectly isolated in the center of the graph is a smooth, delicate, undeniable U-shaped dip.
It gives me goosebumps just thinking about it.
The hidden shadow of a newly born world revealed by mathematically silencing its host star.
It represents a monumental leap forward in photometric analysis. And once EDE successfully cancels the noise and reveals those hidden planets, it can finally perform the task it was built for, counting them. Which brings us to the ultimate scorecard.
The moment of truth. EVE is staring at 20,000 young stars. The noise is canceled, the data is clean. We are essentially running a grand cosmic experiment with two incredibly clear divergent outcomes.
Exactly.
Let's lay out the win-loss conditions for these two warring scientific factions. What is the expected outcome if Hypothesis 1, the shrinking gas dwarf theory, is the reality of our universe?
If the evolutionary model is correct, if all protoplanets aggressively accrete massive hydrogen envelopes and the universe routinely pumps out nothing but puffy gas dwarfs that haven't had time to boil away yet, then the 20,000 young stars EVE observes should be absolutely teeming with massive, easily detectable sub-Neptunes.
Because they're big targets.
Exactly. Because these planets are large, they block a substantial fraction of light, making them relatively easy to spot even against residual noise. Statistical modeling of the EVE mission parameters predicts that if Hypothesis 1 is right, the telescope will detect and confirm roughly 100 small young exoplanets.
100 planets younger than 50 million years old. That is an absolute goldmine. That single mission would quintuple humanity's entire catalog of young planets.
It would change the field overnight.
But what happens if the data supports Hypothesis 2? What if the sub-Neptunes aren't puffy gas dwarfs waiting to be sunburned, but are actually those dense superyonic water worlds that formed beyond the snowline?
If the dense water world theory is the reality, the architecture of the young universe looks profoundly different. The super-Earths form inside the snowline, and because they are born entirely of dry rock, their physical radii are inherently small. The sub-Neptunes form outside the snowline, but because they are composed of dense, high-pressure ice and rock, rather than incredibly puffy hydrogen gas, their intrinsic physical radii are also relatively small compared to a gas dwarf.
And as we established earlier, the physical size of the planet is the limiting factor in the transit method.
Exactly. The transit depth is proportional to the square of the planetary radius. If a planet is physically small, dense, and compact rather than puffy and extended, the amount of starlight it blocks is microscopic.
Even with the noise cancellation.
Even with a revolutionary NUV noise cancellation technology, there is a fundamental photometric floor. EVE cannot perform miracles. If the dense water world theory is correct, the vast majority of the young rocky and icy planets will simply be too small and their transits too shallow to ever rise above the absolute baseline noise floor of the young host star.
They will just remain hidden in the glare.
Yes. In this scenario, the statistical models predict a brutally low yield. If Hypothesis 2 is correct, EVE expects to find only about 5 new young planets out of those 20,000 stars.
5. Compared to 100.
It is a stunningly divergent set of expected outcomes.
It is exceedingly rare in the history of science that you get such an unequivocally clean, unambiguous verdict. Usually, scientific debates are settled by agonizing degrees. You launch a multi-billion-dollar probe to test a theory. The probe returns data showing a subtle 4% deviation from the expected norm.
And then the academic community spends the next 2 decades arguing in journals over statistical significance and instrumental error.
It's exactly. But this, finding 5 planets versus finding 100 planets, that is a night and day verdict. There is no gray area.
None.
If EVE launches and 2 years later the team publishes a paper announcing the discovery of 95 sub-Neptunes, the debate is instantly over. The gas dwarf camp wins, the universe boils atmospheres, and the champagne is popped.
Right.
If they publish a paper saying they stared at 20,000 stars and only found 4 planets, the Waterworld camp claims absolute victory. The snow line dictates destiny. The debate dies on the spot.
It is a definitive, uncompromising crucible for planetary theory. However, we must ground this discussion in the current realities of aerospace engineering and funding. EVE is a phenomenally well-designed architecture, but as of right now, it is merely a blueprint.
Ah, the catch.
The project has been proposed, but it is not yet fully funded and integrated into a launch manifest.
Right. It's competing for resources.
Yes. EVE is designed and pitched specifically as a NASA Small Explorers mission, or SEFX. And understanding the philosophy behind the SAMX program is crucial to understanding the future trajectory of astrophysics as a whole.
I know NASA has different tiers of missions, like the flagship missions. How does a SMEPNEX mission differ from something like the James Webb Space Telescope?
They represent opposite ends of the philosophical spectrum of spacecraft design.
Yeah.
Flagship missions like JWST or the Hubble Space Telescope before it are designed to be general-purpose, jack-of-all-trades observatories. Right. They cost $10 billion, they require 2 decades of engineering and political wrangling to build, and because they cost so much, they are obligated to serve the entire global astronomical community.
They have to do a little bit of everything.
Exactly.
Yeah.
JWST has to be capable of looking at the atmospheric chemistry of an exoplanet on Tuesday, the accretion disk of a supermassive black hole on Wednesday, and the formation of the earliest galaxies on Thursday. It is a multi-tool.
It has to do everything reasonably well to justify the price tag.
Precisely. A SEMX mission is the absolute antithesis of a flagship. The Small Explorers program is built on a philosophy of aggressive, highly specialized targeting. The budget is tightly capped, usually in the low hundreds of millions rather than billions. The development timeline is drastically compressed.
So it's lean and fast.
Very. And the trade-off for this speed and affordability is that a SEMP mission is not allowed to be a jack-of-all-trades. It is designed, from the silicon up, to answer one specific, profound question, and it ignores everything else.
So EVE fits right into that.
EVE is the ultimate embodiment of this. It does not care about quasars. It does not care about dark matter. It cares about pointing a multi-band photometer at 20,000 young stars to count from 5 to 100.
It's a scalpel instead of a Swiss Army knife.
And that scalpel approach is gaining immense traction. The scientific community is realizing that as our questions become more precise, like the nature of the radius valley, we can no longer rely on general-purpose tools to provide the necessary resolution.
It makes sense.
If EVE is adopted and flown, it will do far more than just declare a winner in the exoplanet debate. It will physically validate the entire methodology of multi-band photometric noise cancellation. It will provide a permanent, proven engineering template for taming the chaotic light of young stars, opening up the entire field of primordial planetary observation.
So, after this incredible journey into bimodal distributions, the crushing thermodynamics of superionic water, the brutal reality of extreme ultraviolet atmospheric stripping, and the ingenious engineering of the 3-sensor solution, let's bring the focus entirely back to you, the listener.
Good idea.
Why does understanding the mechanics of a statistical gap in a catalog of alien worlds matter? Why should the outcome of the EVE mission change how you perceive the night sky? Because answering this single question, whether planets routinely have their atmospheres violently boiled away, or whether they are born as bizarre, high-pressure, half-water, half-rock hybrids, fundamentally rewrites our understanding of what a normal planet actually is.
It completely shatters the geocentric bias we have held since the dawn of astronomy.
Exactly. We all grew up studying our own solar system. We observed the architecture of our local neighborhood. Small, dry, dense, rocky worlds close to the sun, Mercury, Venus, Earth, Mars, and massive, volatile-rich gas and ice giants far away, Jupiter, Saturn, Uranus, Neptune.
That's the textbook picture.
For decades, humanity operated under the assumption that this was the standard cosmic template. We assumed our solar system was the blueprint for the galaxy, but the discovery of the radius valley proves that the universe is doing something else entirely.
It really is.
The cosmos is aggressively sorting billions of worlds into super-Earths and sub-Neptunes, 2 specific classes of planets that do not even exist in our solar system. We are not the cosmic standard. We are the weirdos.
Which leaves us with a lingering, deeply provocative philosophical implication to consider. Let us assume, for a moment, that hypothesis to the dense water world theory is ultimately proven correct.
Okay, let's assume that.
Let us imagine that EVE launches, cancels a noise, finds only 5 young planets, and conclusively proves that the massive population of sub-Neptunes sitting just beyond the Radius Valley are indeed composed of 50% water by mass, forged in the freezing depths beyond the snow line.
If that turns out to be the reality.
If the dominant planetary manufacturing process of the universe routinely and consistently builds worlds that are half water by mass, what does that mean for the prevalence of water and potentially life across the cosmos?
That is a huge question.
Humanity proudly refers to Earth as the ultimate water world, the rare, life-giving blue oasis floating in a sterile, dry void. But if these dense sub-Neptunes are the statistical norm, our perspective is entirely inverted.
We'd be the odd ones out.
We might actually be a dry, arid, rock-hard anomaly in a galaxy that is literally overflowing with deep, planetary-scale oceans. Oceans so unimaginably deep and heavy that the water crushes itself into glowing metallic hot ice.
That is a staggering paradigm shift.
And if the Milky Way is teeming with these incomprehensibly deep water worlds, it forces astrobiologists to confront a terrifying question. Does an abundance of water make the existence of extraterrestrial life more likely because the fundamental solvent of biology is everywhere? Or does it make it drastically less likely because those crushing high-pressure supersonic ice environments are simply too alien, too gravitationally hostile, entirely lacking the shallow sunlit tide pools, the exposed silicate rock, and the wet-dry chemical cycling where we believe life on Earth first sparked into existence?
Are we the only oasis in the desert? Or are we just the only shallow puddle in a universe dominated by bottomless, crushing oceans? That is exactly why the pursuit of missions like EVE is so critical. Because untangling the physics of the Radius Valley doesn't just categorize dead rocks, it establishes the physical boundaries for the search for life itself.
Exactly. It's about finding our place in the universe.
We started this conversation talking about how much human intuition craves smooth, continuous bell curves. The universe, it turns out, actively resists our attempts to put it into neat, predictable boxes. It hides its most profound mechanical secrets behind the blazing, chaotic glare of volatile young stars and buries them under the crushing depths of alien oceans. But piece by piece, algorithm by algorithm, we are building the exact tools required to pierce that glare and read the history written in the starlight. Keep looking up, keep questioning the unseen forces shaping the cosmos, and we will catch you on the next intellectual adventure.